It's a pleasure to speak with everybody here today. I've been researching computing performance one way or another for my entire 50-year career as a computer scientist, starting in graduate school. And I've been teaching an undergraduate class on software performance engineering at MIT for over 15 years. And today I'd like to share with you why I believe software performance will play a huge role in computer science and AI over the coming decades, and a little bit about why you should care. So just to understand what software performance engineering is, it's a fancy name for the science and art of making code run fast, okay? Or otherwise limiting a program's consumption of resources such as power, memory footprint, disk accesses, response time, etc. It involves a host of techniques over that go the breadth of computer science, everything from things like parallelism and caching to algorithmic techniques such as data representation, taking advantage of sparsity, algorithms, to metaprogramming, AI coding, etc. Whatever you can do to make your code run fast. But it's about software, not about hardware. Although you got to know hardware because you're programming hardware. But before I dive into software performance engineering specifically, I'd like to ask kind of a question that I asked myself years ago, what is the value of performance? Okay, and some people say, well, oh yeah, of course we care about performance, but I always start my class out at MIT by trying to give the students some perspective and posing a performance paradox. I ask the students what software properties might be more important than performance. Okay, so there's a lot of sorts of performance is one of them, but there are a lot of others. Okay, so here are a few. Okay, correctness, does the program provide the right answer? Functionality, does it do something interesting? Security, is the program resilient to, where's my cursor? There it is. Is the program resilient to malicious attacks? What are some more software properties that are important? Just shout them out. Maintainability. What else?
Elegance.
Elegance. What else? Readability. What else?
Portability.
Conciseness. Portability. Great. Sorry? Scalability. Modularity. Okay, yeah, I mean, there are a whole bunch. Some of them are ones you folks said, and there are many more. There's probably 100 things. At this point in my class, I invite my students to get up and walk out of my class because MIT offers other classes that address all these other properties. Clearly, they should be taking more important, taking classes on what's most important. And software performance engineering doesn't seem all that important compared to all these other ideas. Let me just mention, no student has ever walked out. They've walked out maybe later, but they don't walk out at that point. Okay. So that's the paradox. If programmers are willing to sacrifice performance for these properties, why study performance? So to think about this question clearly, I invite them to play a game. And I'd like to play that now, okay? And for that, I need a volunteer. So raise your hand, of course, if you haven't seen my talk before, okay? And you're willing to come up here and you want to play a game called Choosies with me. So who would like to play Choosies with me? I guarantee you're not going to get hurt. You're going to go away. Thanks. Okay, come on up. Come on up.
How hard can it be?
How hard can it be? Exactly. Okay. So this is a very simple game. What's your name?
Skip Thunderbolt. Mac.
Mac. Hi, Mac. And you're from Future Labs?
Yes, sir.
Okay, you can face the audience there. Good. Okay, so we're going to play this game called Choosies.
Okay.
I'm going to show you two objects, and you get to choose one, take it back to your seat. Okay?
Okay.
Pretty simple, right? That's the whole game.
That's all I
Okay?
gotta do?
That's all you got to
Do I
do.
get an A?
And you get the thing that I think. So here's the first object. Okay, here you go. That's one object.
All right.
Okay. So that's object number one. Okay. Or you can have object number two.
Yes.
Which would you like? Okay. You made your, now, but wait a minute. Isn't water essential to life?
Yes.
It's pretty useful stuff.
Yeah, it is.
Okay. Could you live without water?
No.
Could you live without $10?
No.
So that's kind of curious, right? That's a paradox, right?
That's right.
And yet you valued the $10. Why did you value the $10 over the bottle of water?
Because I got a bottle of water on my seat.
Yeah. And even if you didn't have a bottle of water in your seat, what?
I still like $10. I go buy one.
You go buy one, right. In fact, you could buy more. In fact, you can buy, I discovered at the local Star Market grocery store, you can get a case of 24 bottles for $5.69, which is less than 24 cents each.
Okay.
Okay? It's all yours. Thank you. Now, of course, there are times when you would prefer a bottle of water to $10. When might that be?
You're in the desert.
Okay. So this picture was generated by Google Gemini. Okay. You can see some artifacts in the water sign. I'm not quite sure what water $, $10 each is, but that was the best I could do in the limited time I had, okay, to illustrate that, yeah, sometimes it is worth $10. Sometimes you'd rather have the $10, sometimes you'd rather have the thing. Well, what's this got to do with performance? Well, the first thing to understand is this harkens back to the origins of economics and Adam Smith's paradox in his Wealth of Nations treatise. And he said the word value, it is to be observed, has two different meanings and sometimes expresses the utility of some particular object and sometimes the power of purchasing other goods which the possession of that object conveys. The one may be called value in use. We sometimes use the term utility. And the other value in exchange, for which we often will use the term price. The things which have the greatest value in use have frequently little or no value in exchange. And on the contrary, those which have the greatest value in exchange have frequently little or no value in use. Nothing is more useful than water, but it will purchase scarce anything. Scarce anything can be had in exchange for it. A diamond, on the contrary, has scarce any value in use, but a very great quantity of other goods may frequently be had in exchange for it. Okay? So Smith goes on to explain that value in exchange is determined by supply and demand and not by value in use. And that's why that's why it makes sense to exchange things, because the value, a shoemaker doesn't need an extra pair of shoes. A miller doesn't need more flour. Oh, let's exchange. Okay? Then they each get something that is valued more to the other. And then, of course, we have the notion of a currency, which is a medium for exchange. It's kind of a platform by which we can exchange. We don't have to, I can exchange something with you, let's say $10, okay? And you can decide you want the to use $10 for something completely different other than what I might be buying or selling. Okay. So what does this have to do with performance? Well, this is the same idea. Okay. We talk about these values of properties of software that are more valuable than performance. Okay. But really, what we're talking about, there are times when you would prefer more performance. Why? So you can spend it on other things. Okay. And in some sense here, the analogy is that performance is our currency in computing. It's what we spend in order to get all the desirable properties we want. We're willing to program in a highly inefficient language for execution, such as Python, wasting enormous amounts of performance because we value the ability to code things quickly. Okay? So that's why we're interested. But there are times when I don't want to program in Python. I want to program in C++ because I'm going to get something more efficient. Okay? And I make that change. And that way I have other performance left over for other things, like response time. I want my calculation to come back quickly or whatever. Okay? So performance is like money. And performance is, in fact, something you can often use to buy needed software properties. Now, of course, just as with money, money isn't alone the only thing that matters. There are other things that matter, okay? But it is one of the main things that we use for trading. You know, very famously, for example, Apple made the decision to waste an enormous amount of performance on their user interface, okay, with the introduction of the Macintosh. Okay, actually the Lisa before that, but in any case, they decided, and the same decision made at Xerox with the precursor, the Alto system, was not taken on by the Xerox executives at the time because it cost more in performance than what they could get with something that didn't have as fancy an interface. Okay? And they basically made the wrong decision, history would argue. Okay? So in the context of computing, the power of performance is that you can exchange it for more valuable things. It has no intrinsic utility, but it can be easily traded for things we care about. We can often introduce layers of abstraction, lots of security checks or expensive encryption, or automate things to get all these other software properties. But in doing so, we're trading performance. And the history of computing is all about increasing performance to gain leverage for more functionality, productivity, security, and everything else, okay, and including AI. Now, for years, computer performance was delivered largely by what Carver Mead called Moore's Law, an economic and technology trend that talks about the growth of performance from year to year. Okay? Moore's Law predicts that the number of transistors on a semiconductor chip grows exponentially. So what's plotted here is the number of transistors on Intel microprocessors over the years. From about 1970 until 2015, the number of transistors on a chip doubled every 2 years. Okay? And this trend was remarkably stable, you know, over all those decades. Okay? Every 2 years, our computing capability doubled. And that's way more than the historical rate of inflation and the growth of the stock market. In fact, it's much greater than my income has grown over that period of time. Okay? Imagine, you know, if your income doubled every 2 years and inflation remained at just a few percent. Now, in 1993, I was the network architect for, at the time, was the world's most powerful computer, the Connection Machine CM5, one of the first so-called massively parallel computers. Because of Moore's Law, my iPhone, which I bought a few years ago, is more powerful than the most powerful supercomputer in 1993. Okay? This phone, okay, in any way you can measure it, memory, bandwidth, flops, whatever you want to measure, except maybe weight. Okay? And it's a lot cheaper too. Okay, that was $47 million. Okay, this cost MIT about $1,600. Okay. Without Moore's law, had it ended 20 years ago, there are an enormous number of things we would not be enjoying today. Of course, would we miss them? Probably not. But now that we have them, we wouldn't want to go back for many of these. Well, some of these you might want to go back on. But so from that point of view, Moore's law was a printing press for performance. Okay? Every 2 years, you got as much compute as you had in the history of computing. Amazing, okay? But as we all know, Moore's law is over. And I don't have time here to go into all the reasons why it is over, and it's definitely over. But let me tell you what we should be thinking about now. About 5 years ago, in the midst of at the beginning of COVID, my really well-timed here for a paper that you want everybody to read, right? It's like, let's do it right when COVID is hitting and nobody has time for anything else. My MIT colleagues and I completed a study about the post-Moore era. We asked, at that time, where will computing performance come from? This is one of these distressing kinds of things, because one of the things that slowed it down was our arguments with the editor, because we said Moore's law was over. And they said, well, you can't say that. And we're saying, like, we got a Turing Award winner on our thing. We have all these people at MIT, and this editor is saying, you can't say Moore's law is over, that's controversial. And I'm like, okay. So we never say in the paper that Moore's law is over. We just say when it's over, here's where you're going to get things. And the idea is that that there's a lot of, whereas we used to get performance from semiconductor technology at the bottom of the technology stack, now there's a lot of opportunity at the top of the stack. Okay? Mainly because we've been so inefficient, because there was no point in optimizing. It's kind of like, if you're on, if your salary is growing at a ferocious rate, you don't bother to cut costs. There's much better things to do with your time than cut costs. You make more money. Okay? But when you retire and go on fixed income, suddenly costs make a big difference. That's the way you make money, is by controlling your costs. And so we looked at 3 areas that we saw opportunities for. Software, algorithms, and hardware architecture. Now, actually, I like to include algorithms in software performance engineering, but for the purpose of this paper, we separated it out. Let's observe that making improvements to hardware architecture is going to be limited to very few people, those people who design hardware and have access to semiconductor foundries. Okay? There's just a few people who can really make any difference there. It turns out to make a contribution to algorithms, you need to be really smart. Few people can really contribute a novel algorithm. Okay? But software is available to a vast number of people. In the United States alone, there are 1.7 million individuals employed as software developers, and many more people than that code. They just don't have software developer as their, as the title of their job. So software performance engineering is the democratic opportunity. Anyone can do it if they're educated to do so. In fact, this has now recently been recognized by the CRA. The CRA is the Computing Research Association. It's the organization of all the department heads in computer science across the nation. Every 4 years, the CRA makes recommendations to the incoming Congress and President. And one of their recommendations is to invest in research, education, and workforce development for software performance engineering. Okay? We'll see whether it has an impact. They do it every 4 years before the election so that it's nonpartisan what the recommendations are. But to see what the impact of software performance engineering recently we had the Chinese AI company DeepSeek shook up the tech world by producing an ostensibly low-cost LLM. Although some argue that their claims are overblown, nevertheless, the U.S. stocks lost nearly $1 trillion led by NVIDIA, which alone lost almost $600 million in market cap. Now, the news reports didn't delve into exactly how DeepSeek managed to achieve its results, but the code is open source, and the research papers make it clear that software performance engineering is key. They did things like, rather than coding in CUDA, they reverse engineered and actually coded the GPU things in assembly language for the machine, which saved them a lot. They could do things, even though they were using older hardware. Okay, but I still couldn't resist asking R1, which is the DeepSeek LLM itself, you know, how important was software performance engineering to DeepSeek's success? And DeepSeek responded, and this, by the way, is exactly the question I typed and exactly what I got back. Software performance engineering was crucial to DeepSeek's success. It ensured that the platform could handle large-scale data processing efficiently, deliver fast response times, and maintain high reliability under heavy workloads. By optimizing performance, DeepSeek was able to provide a seamless user experience, scale effectively, and meet the demands of its growing user base, which were key factors in its competitive edge and overall success. Now, what the stock market, I think, eventually kind of realized, but at the time did not, was that all the techniques, it wasn't like DeepSeek's use of software performance engineering was an alternative to using NVIDIA fancy chips. Okay, it was complementary. Okay, everything that they did for the older chips that DeepSeek was programmed with, you could do with the more modern chips. It's just saying, look, there's a lot more performance than we're getting out of our AI chips today. Okay? And the point is, the way to get it is with educated people who can do software performance engineering. Now, we have many research projects at MIT involving software performance engineering. And I'd be happy to talk with people afterwards who have an interest in any of the specific ones. But I wanted to kind of give a higher level talk here. So rather than running through them, I'd like to acquaint you with a larger effort. We've been working over the last couple of years to build a community called Fast Code, which is dedicated to advancing software performance engineering. The participants and sponsors have been growing. You know, as Alan Kay and possibly others said, the best way to predict the future is to invent it. So together, we're looking to invent a rosy future for computing by developing the field of software performance engineering. And as I say, I'd be happy to talk with anyone offline about some of the specific projects in my research group, which include things like, you know, AI coding, using AI to write fast code, okay, to take code and make it run faster, as well as a lot of work on compilers, algorithms, runtime systems, and on, caching, parallelism, etc. So if you're interested in exploring the fast code effort, please fill out this short survey. This year, 2025, is an exciting time for many reasons we don't necessarily want to dwell on, but all those things aside, it's an exciting time for software. And I hope that people will get involved, realize how important it is to get really good software people in your, software performance engineering people in your company. In fact, I've been working with Neil Thompson to analyze the database of job applications. And it turns out that people with software performance engineering in their background command a premium over ordinary software engineers. And in fact, it's quite comparable to what you get if you have machine learning in your background, and with nowhere near the marketing push. So, and in fact, we now have some data that shows that for every 10% increase that you give in additional fraction of your engineers who do software performance engineering instead of just software engineering, it results in about a 1% net profit increase for the companies that are involved. And that's a study that's just preliminary stuff, so we still have a lot of stuff to do, but very, very interesting, the kinds of impacts you can have in companies for having software performance engineers. So I hope you get involved, and let's print some performance currency. Thank you.